Okay, there is a current in the circuit, which is this mesh current. So let's label it ISC, and then that way I'm sort of saving myself a few lines maybe of, I don't know. I mean, I could have labeled it I1 and then notice at some point I1 is equal to ISC, but anyway, I think I'll just label it ISC. And then this one I'll label I1. Okay, so I'm done with step 2. I've labeled the mesh currents. Dependent source. Well, it's the same idea. We have a dependent source, 10Ix, and it's dependent on a current. So what you want to do in this step is you look at the controlling quantity and you write it in terms of, in this case, fill in the blank. What do I write it in terms of? The mesh currents. The mesh currents. So can I write, okay, so Ix, oops, I forgot to label that. Ix is right here. Can I write Ix in terms of mesh currents?
It's I1.
Yeah, it's I1, easy. Ix is equal to I1. All right, I'm done with that. So since we only have one dependent source, you're just going to have to find one controlling quantity. So the controlling quantity in this case is Ix. I'm writing in terms of mesh currents, so I see here, oh, Ix is just equal to I1. Great. All right. The fourth step has to do with super, in this case, meshes. So what you have to do in that step is identify if you have any super meshes, and then write an equation. So do we have any super meshes? Yeah, we do. Because a super mesh is any current source and the mesh is on either side. So we do have a current source. And so let's just draw the dotted line. There's our super mesh. And for the purposes of this step, we're supposed to look inside of it and do something.
In terms of the mesh current.
Good. You write the current of the current source in terms of the mesh currents on either side. So in this case, the current here is 0.9. And so that's equal to ISC minus IS1. IS1, just I1, sorry. Okay? All right, so I'm now done with that step. Because that step, the super step, you just identify any super mesh that you have. In this case, we only have one super mesh, but sometimes you'll have a problem with more than one. But we've only got one here. And after you identify it, then what you have to do is you write the current of the source in terms of the mesh currents on either side. So that's what I just did. Now we're on the last step. And the last step says that you should write, okay, so in the mesh, in the node voltage analysis, we needed to write Kirchhoff's current law for all the non-reference nodes. For the mesh current analysis, you write Kirchhoff's voltage law for all meshes, okay, and here's the clincher here, that don't have a current source on the perimeter. We've only got one mesh in this problem. It's a super mesh. And it has a current source on the perimeter. So actually, we're not even going to write Kirchhoff's voltage law. We're just going to notice that the current, wait. I actually did this with node voltage analysis. So let me see what's going on here. Oh, this is a weird problem. Okay, because this current source is ISC. Okay, so we didn't even do Kirchhoff in this case because we only had one mesh and it had a current source on the perimeter, so you don't do Kirchhoff's law in that case, Kirchhoff's voltage law. But But you do notice that the current, and the reason you don't need to, well, you can't do it because I wouldn't know the voltage across here. So I wouldn't have been able to do Kirchhoff's voltage law. If you tried to do it, you would have run into a problem. But because you have this on the perimeter, you actually know that the mesh current inside is equal to it. So you have that to use. And now I've got, well, you could think, you could look at this and say you've got 3 equations and 3 unknowns, or if you just substitute I1 for IX, you've got 2 equations and 2 unknowns. Regardless, we have enough equations and the right number of unknowns to solve. So math, math, math. You can solve those 3 equations and you should get ISC is 1 amp. And so then, going back to the Thevenin resistance, which was VOC over ISC. VOC was 3 volts, ISC is 1 amp, 3 ohms. So, I mean, I erased it, but then, so the Thevenin equivalent circuit, that open circuit voltage is 3 volts. The Thevenin resistance is 3 ohms. And so the maximum power will be delivered when RL is 3 ohms, because that's the maximum power theorem. Oh, are we happy? More or less. What time is it? I got 8 minutes to spare. Any questions?
Can we not have the benefit of having the dependent current source be ISC
And still solve
do
it?
and do that last step, the step that we got to skip, where you said we write KVL for all meshes that
Well,
don't have a current source on the perimeter.
Right. I'm not sure what you're asking.
We didn't do that step. We didn't.
Well,
write-
we didn't do it because we're
Didn't
not
need to.
allowed to do it. Because the whole, what this step says is to write Kirchhoff's voltage law
Right.
for all meshes that don't have current sources on the perimeter. So in this particular problem, we only have one mesh. It's the super mesh. It has a current source on the perimeter, so
you write 0.
we're not allowed to do that step in this particular case. That's why it was a little bit of a weird problem and it kind of threw me for a second. But okay, so we're not allowed to do that step. But then what you do instead
Yeah.
is you realize that, oh, we don't need to do the Kirchhoff's voltage law because we know that this current on the perimeter is equal to the mesh current. And so that gave us the last equation that we needed. If you didn't quite have it right and you thought, oh, I'm going to do Kirchhoff's current voltage law around this mesh, you would run into a problem. You would be fine here, right? Because you just have 2ix minus 16. What do you do here? You don't, remember, this is an ideal source. Even though it's dependent, it's still ideal. You do not know the voltage here. So you would run into that problem and then you'd say, oh, what am I supposed to do here? And then you'd remember, oh, well, that last step, you're not supposed to do Kirchhoff's voltage law if you've got a current source on the perimeter of that mesh. So, okay, there was a question up there.
Isn't that C 0.1 amps?
Wait, say that again?
I think I see it's 0.1 amps.
0.1 amps. What do you mean?
Oh,
Oh, you mean the answer?
Yeah.
Well, unless I did the math wrong, my solution, I have it as 1 amp. Pretty sure it's 1. Because I did the solution and I'm never wrong. Okay, so we know that, just because I do have 5 more minutes, we know that the maximum power will be delivered when RL is 3 ohms. Let's go one step further and find out what is it? What is the power? Well, okay, so this is the circuit. What's a TH? How do we figure out the power delivered to this resistor?
C squared over
Power is what?
V squared over R.
V squared over R, okay. And R is RL. V is this V here. Let's call it VL. Okay, but we don't know VL. Or, I mean, we can easily figure it out. I mean, I think you could almost do it in your head.
I squared R?
Pardon?
Can you do I squared R?
You could do I squared R. Okay, so I'll call it IL. And then you could say I squared R. But we also don't know IL.
But wait, isn't it's it's 3 ohm resistors? So it's half the voltage
Right,
on each
so,
one.
yeah,
it's
I'm not saying it's hard, I'm just saying, let's do it. So, so IL, I mean, you can just do it almost by inspection. These are 2 resistors in series, so the total resistance is 6 ohms, and so the current is going to be 6 divided by 3. So 2 ohms, 2 amps. Okay, so now you've got IL. Actually, let me put it in terms of VL, or VOC. 2RL, just because I know there's a formula that you have. So it's basically twice RL divided by VOC. And if you just plug that in here, you would get, am I doing this right? I is VO, I have it upside down.
Yeah.
Yeah, sorry. VOC over 2RL. Let's not call it RL, let's call it RTH, right? Same thing. RL is equal to RTH. So, VOC squared over 4 RTH squared times RTH. So there's a formula that you can use, but it's easy enough just to derive it rather than memorizing formulas. That's if you want it in terms of the open circuit voltage. If you wanted it in terms of the short circuit current, then you would just substitute for VL here. And using a voltage divider, I mean, okay, these are 2 equal resistors, it's just going to be half, so it's going to be 1.5. So or VOC over 2, so you could also put the power in terms of VOC over 2 squared over RTH. Oh, wait. That's the same thing. How do I get it in terms of IL? Anyway, you can do it. I'm done. Any other questions? All right then, thank you.
Come back, the different perspective is useful.
Yeah, I always found that with different teachers. Yeah. All right. I have another class to go to. Okay.